test provides a single, flat average of blood glucose over months, but the raw data from a continuous monitor reveals a different reality, a system in constant, erratic oscillation. The Newtonian framework in medicine treats this natural physiological variation as random noise. It seeks to smooth these fluctuations into statistical averages, obscuring the actual dynamics of the system. Human biology is not a series of linear mechanisms designed for a stable equilibrium. It is a multi-scale, adaptive system operating far from thermodynamic balance. Healthy biological systems actually thrive at the edge of chaos. They utilize high-dimensional complexity to maintain the flexibility needed to navigate environmental and nutritional stress. But in metabolic disease, the system's healthy chaotic flexibility collapses, dropping the physiology into a rigid, pathological attractor. Because standard clinical metrics are non-ergodic, they cannot detect the subtle loss of fractal complexity that occurs long before a patient experiences a catastrophic metabolic shift. Preventing that collapse requires a shift from reactive symptom management to proactive dynamical control. We treat the human body as an advanced chemical plant. To survive, it requires a closed-loop architecture that synchronizes neural, immune, and metabolic activities. First, we define hardware limits by mapping the individual's genetic boundary conditions. Second, nonlinear sensors monitor the system's trajectory in real time. Third, targeted stoichiometric inputs act as a corrective actuator, steering back to stability. Clinical systems biology uses this architecture to predict and steer patients away from pathological bifurcations before the systemic damage becomes completely irreversible. Before we can steer a complex system, we must define the inherent hardware limits of its metabolic network. The Ayurvedic Genomics framework establishes these limits through Prakriti, mapping multi-omic correlates that define an individual's metabolic and signaling baseline. A Pitta-dominant phenotype, for instance, correlates with extensive metabolizer genotypes in the CYP2C19 gene, which facilitate rapid enzymatic transformation and intense immune inflammatory responses. This genetic reality allows for high metabolic flux and rapid adaptation to oxygen variations through sensors like EGLN1. In contrast, the Vata phenotype is molecularly linked to rapid synaptic signaling and high cellular turnover, while the Kapha phenotype correlates with poor metabolizer genotypes and lipid accumulation. These genetic markers define our enzyme flux bounds, the physical and chemical limits on how fast biological reactions can proceed within the system. We program these bounds into whole-body metabolic models to simulate a patient's individualized capacity across 26 distinct organs. Identifying these boundaries ensures the intervention never pushes the metabolic engine past its biochemical limits, preventing the cumulative wear and tear known as allostatic load. Static biomarkers are often trailing indicators. By the time a standard test crosses a clinical threshold, the regulatory network may have already begun to fail. We instead look for critical slowing down, the measurable loss of network resilience as a biological system approaches a catastrophic tipping point. We detect this through digital noddy monitoring. Sensors capture the arterial pulse wave at 500 Hz to analyze nonlinear dynamics. The signal decomposes into percussion, tidal, and dicrotic waves, tracking vascular resistance, arterial compliance, and peripheral signaling. While healthy physiological signals are chaotic, a system approaching metabolic syndrome exhibits a sharp drop in its fractal dimension. This loss of complexity is quantified as a plummeting approximate entropy score. The biological signal is becoming dangerously regular and predictable. Clinically, this manifests as a sluggish return to equilibrium, prolonged glycemic spikes after a meal, or a delayed recovery of heart rate variability after exercise. This rigid signal is a primary indicator of instability. It proves the biological network has lost its adaptive capacity and entered a phase transition toward pathology. Once a sensor identifies an impending bifurcation, we must intervene in this gap of instability before the system shifts into a stable, diseased state. We utilize the stoichiometric diet, treating nutritional intake as a mathematical control vector to constrain metabolic fluxes. Following the growth rate hypothesis, we adjust carbon, nitrogen, and phosphorus ratios to restore mass balance across the biochemical network. A Vata-dominant system, characterized by high cellular turnover, requires a low carbon-to-phosphorus stoichiometry to provide the phosphorus needed for rapid ribosomal RNA production. Conversely, a kapha phenotype requires severe carbon restriction to prevent the elemental imbalances that drive lipid storage and obesity. This steering provides dissipative resonance. It is an engineered force that deepens the system's health basin of attraction, pulling the patient away from pathological attractors. This architecture protects the most critical feedback loop in the human body, the endocannabinoid, microbiota, neuroimmune supersystem. When these neural, immune, and metabolic signals decouple, a state known as fission, the system loses its ability to translate environmental inputs into homeostatic responses. Formulating the stoichiometric diet with precise molecular inputs, such as short-chain fatty acids, provides the signaling metabolites necessary to reverse this decoupling. These metabolites remodel microbial populations and recouple the fragmented feedback loops of the supersystem, re-establishing network integrity. The Trisutra framework implements this by replacing population-level averages with an integrated specialty practice tailored to the individual's dynamic trajectory. By uniting genomic mapping, NADI monitoring, and stoichiometric steering, clinical systems biology provides a high-resolution method to engineer and maintain biological resilience throughout the life course.